Hi, my name is Nick, and I'm going to be talking about a manufacturing process for lightweighting aerospace and automotive parts using a novel composite material as 3D printer filament. The vehicle manufacturing industry is ever expanding, and there's always a need for higher performance systems, sustainable materials, better fuel economy, and faster production lines. There's many parts in a vehicle, and these can be developed for a 3D printer. Environmental control ducting systems are ducting systems in aircraft, and this is one example for which we can replace old methods of manufacturing with new ones which might have new benefits such as lightweighting, and there are other benefits to introducing 3D printing for these types of parts as well. These parts can be very complicated, and for a single vehicle there can be many different types of parts for the same vehicle. So currently, to manufacture aircraft ducting, it's a very laborious process. First, the material has to be cut in sheets, then it has to be hand laid up by a worker into molds. Then these ducts are cured under pressure, then they have to be demolded, then they have to be trimmed and finished, and finally they have to have thermal insulation wrapped around the outside. But with new manufacturing processes such as 3D printing, maybe this can become a one-step process, and in the process, maybe it can even be a lighter weight product. So these are some prototypes I've made of 3D printed ducting for vehicles, and it shows that you can use very complicated geometries and even create internal structures within the walls of the duct. With 3D printing, currently there's not very much research done on foaming from a 3D printer nozzle, but I'd like to introduce this concept and introduce some 3D printed foam ducts. And here are some examples of some that I printed myself while looking into this research. So when we 3D print foam ducts, one of the benefits of 3D printing is that we can lightweight the ducts in many different ways. And we can do this on different scales, from a macro scale to a micro scale. So here's a diagram I made of some different types of lightweighting we can do. We can use topology optimization to limit the amount of geometric material we use in a duct. On a smaller scale, we can use the 3D printer settings to hollow out walls in the duct. In other words, you can have a double wall duct with an air gap in between instead of a solid material, since you can print internal parts in a 3D printer. Even smaller than that, you can create gaps in layers of raster lines that are being extruded. Each raster line, you can adjust the dimensions vertically and horizontally and how close and far apart they are together. And this can leave micro structures and micro voids which help with the lightweighting process. And lastly, and most importantly, which I'm going to be talking about most, is using foam 3D printer to make very tiny micro bubbles. So currently in 3D printing, there are many materials available, but not all of these materials are high performance enough for vehicle industry use. So the four polymers that are highlighted here, they aren't available commercially for 3D printing. So they need some research development. These types of polymers provide many different types of mechanical properties that are very essential to high strength components for vehicles. So with foam polymers, we can start looking at structures we can make with foam. So to introduce foaming in a 3D printer, I've tested some filaments made with a chemical blowing agent infused, and they're manufactured in a screw extruder, and the chemical blowing agent is released at a higher temperature in the 3D printer nozzle. So what we get when we extrude a string of this material out of the 3D printer nozzle, you can see in these examples the chemical blowing agent is releasing foam and is diffusing at different rates throughout the strand, and we can characterize this through studying it. Here's a tomography test I did with a sample of not just the strings but printed in a simple object. So you can see bubbles in all three orthographic projections, and for the first time we're introducing a foam from a 3D printer in an actual object. So the chemical blowing agent that's released during this process, it's affected by a lot of different 3D printer settings. So one is printing speed. There's many variables that you could change in the printer settings, but there's a few very important ones. Also there's 3D printing, temperature and layer height are very important. The temperature obviously releases blowing agent, and the layer height affects the compression between the layers and the nozzle while it's being extruded. We can also use different blowing agents. So this means we can pinpoint different temperatures we want to release the blowing agent from the nozzle, and we can also possibly control the time, and we get a greater degree of material control from this. So I made this diagram to show how a 3D printer filament with a dense core of chemical blowing agent can solve some of the problems and challenges with having chemical blowing agent in a 3D printer filament. Because if it diffuses very fast, it's such a short window of time, and it's a very small volume of material, that the gas can escape very easily. But my idea is to use a special process to concentrate the blowing agent at the core of the filament, so it has a better chance of diffusing properly while it's being deposited. So the way this filament would be created is in an extrusion line, which I'll show in a minute. But this is the feed block where the two blends of chemicals would join together and create this filament with a shell and a core of a different composite material. So the two materials can even have two different blowing agents. They can have the same one in a different percentage. They can even use different polymers. So to create this, you would mix your blowing agent with raw pellets in the B blend hopper, and this is going to form the core of the filament. Then you need a second hopper to form the shell with a different blend. So this would be a lower amount of chemical blowing agent, but in my experiments I found it's very difficult to print high performance polymers that are very viscous. So by adding some blowing agent into the shell of the filament, it actually allows it to reduce the temperature required for a good melt flow, and it makes the 3D printing easier. So that's why I would put blowing agent in both sides of the process. Finally, where the shell and the core materials meet in the surface layer feed block, it creates the final cross section of the filament, and finally it comes out of the die in a form of a filament ready to be spooled for the printer. So the temperature we would use in in the process of making the film would be lower so that the chemical blowing agent doesn't get released. But then later when we 3D print, we would use a higher temperature and pinpoint that the gas will be released at that part of the process, and we get a 3D printed object. And so, in conclusion, the future of automotive parts and aerospace parts, we could get lighter weight products and really optimize the material. Thank you.